Hey everyone, we're going to take a look at numbers 3 and 4 in section 310. They are related to one another. And I'm going to use the um, information for number 3 on number 4 as well, and I'll explain. We're going to assume that the radius r of a sphere is expanding at a rate of 20 centimeters. That's what cm is per minute. And they give us the volume of the sphere and its surface area. I just want to make a note that you can, on a test, have these formulas on our help sheet, right? You go to the algebra sheet, the bottom is geometry, and you'll see a sphere. For instance, there's the volume, there's the surface area. That A is the area of the exposed surface, how much paint you would need to paint the exterior of the sphere. And you see the other formulas you have for the volume of the cylinder, and all these other um, volumes and surface areas of solids, and then areas and some circumference, for instance, of a circle. And you also have Pythagorean theorem down here. So be familiar with these formulas. These are what you'll have on the test. Okay. So going back to the problem then, for number 3, and again, your expanding rate here could be slightly different. And for number 3, we're to determine the rate of change of the volume, or the rate that the volume is changing with respect to time when r is 15 centimeters. And again, your r could be slightly different, but the problem is basically the same. We're given dr dt, right, which is the rate of change of the radius with respect to time. In my example, it's 20 centimeters per minute, right? The radius of the sphere is expanding at a rate of 20 centimeters per minute. And expanding, so positive, right? Positive is the dr dt. And we're asked to find what? In this case, the rate of change in the volume, dv dt. And we're going to find at the instant when the radius is 15 centimeters. So I'm going to, of course, use the formula for the volume of a sphere. That's the equation that relates our variables of interest. I take the derivative with respect to time, right? With respect to time, both sides. So derivative with respect to time of v is just dv dt. Here, 4/3 pi is a constant. And then when I take the derivative with respect to t of r cubed, I've got to use the chain rule, right? Outer function is r cubed, inner function r. Derivative of r cubed is 3r squared times the derivative of the inner function. Well, with respect to t, derivative of r is dr dt. Okay, clean this up. 4/3 times 3 is just 4. So I get 4 pi r squared. And dr dt, I'm going to go ahead and replace with 20 centimeters per minute, of course. And so 20 times 4, that gives me 80 pi times whatever the radius is squared. Well, the radius we're told is 15 centimeters. So if I plug that in for dv dt, 80 times 15 squared is 18,000 pi. All right, don't forget your pi. And this is going to be cubic centimeters per minute. They give you the units in the problem in Achieve. I'm going to not. You're going to have to give me those units. So you should know we're talking about volume, right? So that's cubic units. Our units are centimeters, so we've got cubic centimeters, and the time units are, of course, our minutes. So you should know these are the correct units in this case. You can also get them if you think about the units, because dr dt, right, this 20 here is centimeters per minute, and then r that we're plugging in here is centimeters, and I square it. So I've got centimeters per minute times square centimeters. Centimeters times square centimeters gives me cubic centimeters, right? Centimeters cubed. Okay, so hopefully that makes sense. Now, number 4, I'm going to use the same rate of change for the radius. Basically, they'll say the same thing, but I think they'll maybe change this rate. I'm going to keep it at 20 centimeters per minute, and this time I'm going to determine the rate at which the surface area is changing with respect to time. And this time when r is 40 centimeters, again, this number changes, might be different than yours, but the idea is the same. Again, we're given dr dt, so I'm going to use that same rate of change that I had up here, whatever it is for you. Find dA dt when r is 40 centimeters. So here's the equation that relates the area of the surface of the sphere to its radius. Take the derivative with respect to t to both sides. Here I get dA dt. Here, 4 pi is the constant multiple. R squared, I got to use the chain rule. Remember, it's the derivative with respect to t. So I'm taking the derivative with respect to t, basically, of both sides of this equation. And so I get the derivative of the outer function is 2r. So bring the 2 down, I get 8 pi r times what? The derivative of the inner function dr dt. Okay. So there's the related rates equation. And now I can find dAdt when R is 40. I just plug in R is 40. And remember dRdt, we're going to be using this one, which is 20. 8 times 40 times 20 is 6,400. And then don't forget your pi. And notice the units now are square centimeters per minute. And that's because we're talking about the rate of change of a area. The surface area is square units. Okay, so make sure you're clear on how to find units. I'm going to ask for units on a test. And you need to be able to give the correct units with your answer, unlike Achieve that gives you the units outside of the box. Okay, I hope this helps with these two problems.